Yeah, so hello everyone. Sorry for the delay. Mm. The first question is: do you have any questions about the problems and about previous lectures?
Just one.
Mm-hmm.
About the eighth problem that you uploaded yesterday.
Mm-hmm.
I tried to go back from the PDE domain after computing all the coefficients. So,
Mm-hmm.
but I was not able to do it because I had a sum, a series over k of some coefficients multiplied by sine of ke, sine of kx, kx. So I suppose it's not summable in a possible way.
But there should be some finite number of terms. I've chosen as functions such that all the series are actually finite. So
I'm not sure because
probably
I got that the coefficients were zero when even coefficients and not zero all the other coefficients of the boundary conditions. Probably, maybe I made a mistake, but.
or maybe well, let me think.
Because there was the square.
Maybe you are right. I wrote such functions. Yeah, I should have chosen some powers which are even or odd, so that the Fourier series terminates. So yes, the problem turned out to be more complicated. So probably I will think more carefully and write a nicer version where everything can be summed. Yes.
Okay.
So in principle you can write a series even in that case, but it will not be nice. Well, so, thanks for asking. So probably I'll add another problem of this kind, which can be solved explicitly. Mm-hmm. Yes. So, any other questions? Mm. Uh, so, oh, by the way, I don't remember. Did you give me your email or not? So probably. But have you seen the previous lectures, recordings? So maybe then, so that I don't forget. The email. So edit this mailing list. So and everyone else. Yes. So, okay. Today I want to tell something about the origin of this all these PDEs, like mm, uh, how they appear in nature or in some mathematical problems. So the first a source of these PDEs are Maxwell's equations. they look like this. Uh, then and so there are four equations. Like for it's for the case of um, of electromagnetic field in some matter. And we should, so in principle, there are four vectors. Um, I, I don't remember precisely how they are called. So this is electric field, this is a magnetic field, and these ones, they should have some names, but those are electric and magnetic fields with corrections related to the fact that we consider matter. Uh, uh, with a linear response. So there are relations between this fields, this and this, and this and this, and it looks like uh, d equals to epsilon epsilon 0 e and uh, h equals to, so let me to 1 over mu 0 b. So in principle, this epsilon and mu can be some tensor. This relation can be nonlinear because it contains also induced charges in matter and induced currents or magnetic momentum. But in the linear approximation, we can write it like this. Uh, so this is called um, dielectric constant, and this is called uh, magnetic constant. So are you familiar with them or not? Mhm. Okay, so uh, mm, now uh, mm, if we want to solve so what can we do now? Um, we can try to solve some of these equations. So, for example, this one, which states, by the way, do you know how to write these equations in kind of four-dimensional form in terms of one forms? Yeah. Yeah. So. Uh, so there is also notation like df equals to 0 and d star f equals to j. So this is equivalent. This is 3 plus 1 way of writing it, and this is four-dimensional. So if we want to solve them, we can write B equals to a rotor or curl of A. Then this equation is automatically solved, and then this equation states that this rotor of E, maybe this, equals to rotor of minus dA over dt. And so, comparing this, comparing the left-hand side and the right-hand side, we conclude that E equals to minus dA over dt plus something which is not sensitive, which is killed by a rotor. And this is gradient of some function plus gradient of phi, oh, minus gradient of phi. Mm. This substitution solves the first pair of equations. And if you do it in the four-dimensional notation, it will mean that we just substitute f equals to dA. And if now and also this A and phi are defined up to the gauge transformation. So a pair of A and phi is equivalent to a pair A plus gradient of f. This preserves this formula for magnetic field. And if you want to preserve a formula for electric field, we should write here phi minus f dot, like this. So if you now substitute it to the second pair of equations, we get what? We get minus Laplacian of phi, well, minus d over dt, divergence of A equals rho over epsilon 0. And no, I'm not sure that I want to do the same with magnetic field. Or maybe, shall we do this? So let's also do this. So here we have a rotor of mm, mm, maybe I'm thinking that probably it was better to start uh, just from writing the Maxwell's equations themselves. Oh, but well, let us proceed. Mm, mm. And here I forgot to divide by epsilon 0, by mu 0. Yes, like this, mm, plus plus j on this pair of equations, and now we need to rewrite this expression. It is done like like this. So yeah, so it's formula for a double vector product. So first this term scalar product of this times this, and then this one times the scalar product of this ones minus Laplacian A. So this equation is written as uh, what is gradient of divergence of A. Hmm? But component-wise Laplacian, because it is so what was written before. It was nabla times nabla acting on A. So it's a differential operator which acts on a vector. So, so here minus Laplacian of A equals to minus mu 0 epsilon 0 d2 A over dt squared plus no, minus d over dt gradient of phi plus j. Uh, so uh, now uh, now what can we do? We see this mm, this a pair of equations for phi and a, which mix them. But remember that physical quantities are B and E, and they do not change if you perform such a gauge transformation with A and phi. Uh, so mm, uh, using this gauge transformation, we can uh, so let me think. Mm, mm, which precise gauge do you want? Mm, yes, so the terms which we don't like are these ones. This one and this one. And there are also there is also this term in this equation. But let us first deal with this pair. So we want to remove them by choosing an appropriate gauge transformation. So Uh, their combination is the gradient of divergence of A minus mu 0 epsilon 0 uh, uh, d phi over dt. And uh,
There is also the gradient of phi.
hmm?
Okay.
Mm. So actually, did I miss some sign? Or probably I did. So why did I put here this minus sign? It is no. This formula is with minus. Sorry. Mm. Hmm? Mm.
Inside the parentheses near the A over the T.
Yes. Thank you. Yes. because and now here we will have plus. Now I like this much better. Much more. So it is 0. So we can ask that gradient of a plus mu 0 epsilon 0 and here was mu 0 epsilon 0 equals to let's define one t. We ask it to be 0. And we should check that we can actually achieve this by appropriate choice of f. So let us check. So this expression transforms to itself plus what? Plus Laplacian of phi, Laplacian of f minus mu 0 epsilon 0 d to f over dt squared. And we see that in order to find this function f, we just need to solve this wave equation with arbitrary right-hand side. So we can do this. We can find such Gibbs transformation which kills this term. This is I forgot how it is called precisely. But in the four-dimensional notation, this gauge constraint looks like this. So if we now use this formula, we can rewrite our equations like minus Laplacian of phi plus mu 0 epsilon 0 d over dt squared phi equals to rho over epsilon 0. And the second equation is mu 0 epsilon 0 d squared a over dt squared minus Laplacian of a equals to mu 0 j. So and now we can see that there is this coefficient in front of 1 over dt squared, and we denoted by 1 over c squared. And this c is a speed of light in a medium with constants epsilon and mu. And in particular, if you consider a vacuum, then this mu and epsilon are 1 for vacuum. And first time it looks like a miracle when you take two constants from magnetism and from electrics, multiply them, and you see that it's 1 over c squared. So using this, we write these equations like 1 over c squared, 1 over d over dt squared, phi minus Laplacian phi equals to rho over epsilon 0, and And this operator is called a D'Alembert operator or wave operator. We see that electrodynamics gives us wave equations with an trivial right-hand sides and functions which are which satisfy these equations are potential and vector potential of electromagnetic field. And you also see that since B and E are some derivatives of these potentials, they also satisfy the same wave equations. Yes, thank you. Yes, thanks.
I have another question.
Mhm.
So, when we impose that part is equal to zero, so we are assured by some theorems that there exists a function f so that condition is respected.
Yes, we just need to solve this wave equation with the left-hand side, and it can be written constructively. We can present a grain function for this.
Depending on the context, we choose that particular function.
Uh, yes.
There's not a usual. Okay, it depends on A
Also, logic is the following. We have this pair of equations for phi and A. And if we start looking for their solutions, their solution is defined up to some arbitrary function f. So it's not fixed. A solution of the system is not unique. It has this infinite functional freedom. Yes. So if we write it in this four-dimensional or differential form notation, we see that this gauge transformation corresponds to A to A plus df. So we try to parameterize closed form as a Dirac differential of some one form, but this one is defined up to Dirac differential of some function. So, if we want to be able to solve something, we can fix this freedom by imposing some extra condition on f. Some extra condition on A, which can be satisfied. So the geometric picture is that we have orbits of the gauge group. By the gauge group, I mean this transformation. A goes to A plus df. And if we get a solution, we get actually the entire orbit. We can get solution plus all such gauge transformations of it. And if we try to fix the gauge, we intersect these orbits with some line. Such that this intersection has a more or less finite number of points. So this is the gauge condition. So there are some tricky questions about this choice of engaged conditions, because this choice does not kill all possible gauge transformations, because we can still use plane waves for this f. But let us uh, uh, forget about this and just look at these equations. Mm, so, so, so we see here the wave equation. Mm. Hmm?
How is the square operator?
Hmm?
Does the square operator properly? How?
The number. Mm, maybe down. Let me check that. Put in this one. Uh, this is the wave equation. But now we can consider some simplifications. For example, if everything is uh, mm, is time independent. Uh, for example, we have some stationary configuration of charges and of currents, and try to find a stationary a solution of this equation. Uh, so if there is no T dependence. So in this case, uh, Mm. We just have minus Laplacian of phi equals to rho over epsilon epsilon 0. So it's just a Poisson equation. Mm. So let me think what else can we do? Mm. Uh, uh, so we can also get we can also consider some configuration uh, of the following kind. So uh, uh, let me think. So there is this Poisson equation. Uh, Um, and we can consider some situation where we have two conducting surfaces, like infinite conducting surfaces, placed at the length L. Uh, well, maybe not the best place to write it. So in this case, and it means that on the surfaces we have phi equals to 0. So if you have such a situation, then we can use we can substitute Fourier expansion of phi, uh, which looks like so phi equals to sum of phi k times sine of pi k over L. And this pi k z over L, and this phi k is depend on x and y. And if you substitute it into the Poisson's equation, it will give us minus Laplacian of phi plus pi k squared over pi k over L squared pi k no yeah pi k equals to some rho k over epsilon 0. This phi k is of x and y. So this is a Helmholtz equation. So each of these modes satisfies its own Helmholtz equation. So are there any questions on this? So let me also show another example which gives us a lot of equations of this kind. So, namely, there are examples coming from hydrodynamics. So, in this case, we have a Navier-Stokes equation. And it looks like this. So we have d over dt plus u gradient u equals to minus gradient of p over rho plus eta Laplacian of u. This corresponds to viscosity. And in principle, we can have, I don't remember the sign, and the name of this coefficient. If it is compressible liquid or gas, we can have such term. So this is an equation for the velocity field. Maybe eta. Well, it's fine. And we also have continuity condition like dρ over dt plus divergence of rho times u equals to 0. And also we should also have some we should have some formula for p. Well, basically we can say that p is p of rho if it is compressible liquid. If it is not, then when rho is constant, we don't have such relation. So, and now let us study several cases. First, let us study incompressible fluid. So, in incompressible liquid. So in this case, rho is constant. And we have here, yes. Yeah. It is the following differential operator. So maybe I'll write it here. And actually, I will use this blackboard to prove some identities. So U number is by definition sum of ui d over dxi. So u nabla acting on u is a sum of ui d over dxi uj ej sum over ij. So is it fine? So this combination d over dt plus u u times gradient is sometimes called dt, and the physical meaning of this quantity is the following. So if you have some field of u, and there is some so we can kind of change. We can kind of choose two different coordinate systems. One coordinate system is just kind of usual coordinates x and y. It's usual laboratory reference frame, but we can also use some local coordinate system which is bounded to the moving element of this liquid. So um, and if you have some quantity which, like I don't know, temperature of a liquid, or in this case uh, it's velocity itself. But let us think, for example, about temperature, about concentration of something. So mm, the cause of a change of this quantity at some fixed point in this laboratory coordinate system can be either because the temperature or some other property of this particular element of liquid changes with time for some reasons. Uh, or it can happen because this element of liquid just moves to this point from somewhere else. And this second phenomenon is reflected by this U-time gradient mm, part. So it is called convective derivative. Mm, So, mm, and this Navier-Stokes equation is actually just just second Newton's law, which which tells us that mm, a change of momentum of this element of liquid equals to the external force. So it can be written like rho dt of u equals to minus mm, gradient uh, of pressure, which is, well, maybe better to write it that it equals to uh, to F. Uh, So we write it for the element liquid, and then if we look at its velocity at a given point, we should take into account that it changes not only because of the action of external forces, but also because we are uh, we are so the element of liquid which is located at point x y changes with time because this liquid flows through this point. So is it more or less clear or not? So it was kind of derivation of this Navier-Stokes equation. So. Hmm. Okay, but now we need to do something with this. So, namely, there is some computation which allows us to rewrite this term in some different form. Uh, so, let us consider. Let us first consider the following quantity. Let us consider u times uh, a rotor of u. So uh, mm, Of course, when we see something like this, we want to use this double vector product identity. But when we do this, we should remember that the gradient is a is a differential operator, and if we look at this equation, this differential operator acts only on this vector. So we should reflect it somehow. So let us add index 1 to this u and index 2 to this u to remember that this gradient acts only here. And now let us use this um, double vector product identity. So this is it. It's this vector times scalar product of this u2 times u1 minus this vector times scalar product of all this. It is u2 times u1. And now let us think what it means. So here everything is fine. Nabla does not act on u2, it acts only on u1. So this is precisely these convective terms that we want. And here Nabla acts only on one of these two u's. But if we ask it to act also on the other u's, it will produce precisely the same term. So we can just add 1/2 and write it like gradient of u squared over 2 minus u gradient u. So that's all. So using this identity, we can rewrite this Navier-Stokes equation as well, so there are continuity equations. U gradient of u equals to 0. So let us write the first one. Du over dt plus plus gradient of u squared over 2 plus root of u times u equals to minus gradient of, in this case, it's just gradient of p over o. Plus eta Laplacian of u. So we have some equation. And let us also introduce a notation that omega is a rotor of u. I don't remember the name, probably it's called vorticity or something like this, or just a rotor of u. And if you want to write some equation which would be the equation for this omega in some sense, we can just take a rotor of both parts of this equation. It will kill the gradient terms, and it will give us d omega over dt plus rotor of omega times u equals to eta Laplacian of omega. So now, if you say that u is how to say it? So if you now say that u is small, then this term is of second order, and the linear approximation to this Navier-Stokes equation is d omega over dt equals to eta Laplacian of omega. So it is a kind of heat or diffusion equation, which says that if you have viscous liquid, then this vorticity field will spread everywhere. So. Mm. So it's one consequence of this equation. And another consequence is the following. That, you see, even if U is big, we can still say that if we consider such initial condition that omega is 0, then it will stay 0 all the time. Of course, if we don't choose such boundary conditions which can create this vorticity. So if omega at t equals to 0 then omega at any time is still 0. And it means that we can consider a so-called potential approximation. No, potential flow. Potential flow is when U is a gradient of phi. And this is called flow potential, so there is some function phi. And if we consider this approximation, then so let me erase this probably. So if we consider this approximation, then from then we can take incompressibility condition, gradient of U is 0, and we get the equation Laplacian of phi equals to 0. So such flows with zero order of U are described by Laplace equation, and it is used in this study of especially two-dimensional hydrodynamics, because so for example, if people try to compute some simplest approximations for the airflow around the wing of the airplane, they solve this equation with specific boundary conditions and try to guess, for example, conformal transformations which map these boundary conditions to something nice and solvable. So mm, there is a quite big field related to study of this. Like at least it was some times ago. So, but it was. Are there any questions about this? Yeah. We asked that density is constant, and so that a second equation, rho dt plus gradient of rho times u equals to 0, gives that divergence of u is 0. Hmm?
Also, in the equation w dt plus nabla squared half, and so on, where we have the triple product. So nabla vector u,
Mm-hmm.
we can write it that way because with cyclic operation the vectorial product is the same because we computed u vector nabla vector u.
Yes, no, but what which cyclic symmetry?
I mean, if I have three vectors a, b, and c, and I do a vector, b vector, c, is it the same as c vector, a vector, b, right? So
A, B,
I apply a cyclic
no,
interpretation.
no. So if you have A times B times C, it can be, so there are two products. One is when both of them are vectors, and you see that by construction this vector is orthogonal to A, and it's actually the linear combination of B and C. So this is B times AC minus C times AB. But there is no cyclic symmetry. But if you consider scalar product times vector product, it equals to volume of parallelepiped spanned by these three vectors, and this one is actually cyclically symmetric. So what's the question?
Because I was asking this because we computed not nabla vector u, but u vector nabla vector u.
Yes.
And
So
yes, we expressed that thing with respect to nabla u squared over a half. Yes. And
yeah.
not that one, but u vector nabla vector u.
Yes. No, no. Ah, fine. Mhm. Oh, oh, okay, so it was one example coming from hydrodynamics, and but there is also another example. Uh, uh, mm, it is for a compressible medium. So in this case, we will have uh, P is some function of rho, and we consider some small fluctuations of density, pressure, and velocity. So, namely, we consider the following approximation: u is u 0 plus some epsilon v. Mm, Rho is rho 0 plus epsilon rho 0 times r0 times let us call it delta rho. So then up to the and also let us say that eta is equal to 0. Oh, and eta prime. So we can modify these equations, but for now let us consider a situation with zero viscosity. So if you now substitute this into Navier-Stokes equation, so what we get? We get epsilon dv. So this u0 is constant. U0 is constant. Rho 0 is constant. So it's a situation, for example, if I have some wings, then a wing of the airplane, and we have, and we are far away from this. So we have some a constant field of velocity u0, and we also have some perturbation of this constant field, and we also have perturbations of density. So this is u0 plus epsilon v. So the first order, non-trivial term in this Navier-Stokes equation will be epsilon dv over dt. Here the leading term will be u0, so epsilon u0 nabla v, and this equals to minus epsilon dp over d rho times delta rho, like dp over 0 over d rho 0 times delta rho, and that gradient. I'm saying that density is expanded around rho 0 like this. So it is well, better to write it as rho 0 1 plus epsilon delta rho. So this a small fluctuation of density. So it is a gradient of delta rho. It's this first equation, and this incompressibility, this conservation of mass equation tells us that d epsilon d delta rho over dt plus u0 nabla delta rho epsilon plus divergence of u, divergence of v equals to 0. Plus some other terms, but we don't care. So
Delta rho is factor.
uh,
In second equation, the flow looks like a vector.
oh, sorry, no, it's scalar equation. In principle, we have some O of epsilon squared, but we don't care. We consider only the leading term. So now we can look at these equations and introduce again this convective derivative, but now it will be just d over dt plus some term with constant coefficients. Zero gradient, zero gradient, such differential operator. And if you do this, these equations can be written like this: dv over dt oh, dt v equals to minus dp over d rho gradient delta rho. The first one. The second one is dt delta rho equals to delta rho equals to minus divergence of v. So now what do we want? We want to get a single equation on the function delta rho. So let us compute the second derivative of the first equation. So we have dt squared. I don't know, maybe. So is it what we want? Let us compute the derivative of the second equation. Dt squared rho equals to minus divergence of dt v. So it's from here. And now let us use the first equation. So it tells us that dt squared rho equals to delta rho, sorry. Delta rho equals to what? dp over d rho. So what should we write here? What will we get after the substitution? If you use this equation and substitute here. Mm-hmm. Yeah, so a number squared is a Laplace operator because number is sum of ek d over d dxk, and if you take a square, it is sum of d2 over dxk squared, which is a Laplacian operator. So it equals to Laplacian of delta rho. So and now let us rewrite this equation explicitly. Let us say that u0 is u0, 0, 0. So so in this equation, d squared delta rho equals to so let us actually call this c squared. It will be a speed of sound in this compressible medium, for example, in the air. This so 1 over c squared dt squared delta rho will equal to Laplacian of delta rho. So if you write it in the components, we will get um, 1 over c squared dt minus u0 over c dx squared minus
Sorry, but c squared is constant.
yes.
So p depends on rho linearly.
No, so there was a function. There was this right hand side gradient of p divided by rho, and I've said that rho is close to r0, and there is some fluctuation which depends on coordinate. So this is dp over d is actually dp over d 0. So r0 is constant.
Rho zero is constant, then the derivation is
Hmm?
rho zero is constant when why the derivative is not zero.
No, because p is some function of rho. So we considered so what we had in the right hand side. Uh, we had p is p of rho 0 was epsilon delta rho, and we took a gradient of this p plus epsilon rho 0 delta rho. We took gradient of this function. So it is p prime times times epsilon times rho 0 times gradient of delta rho. Do, do you agree?
I'm not getting the point, but it's fine.
Oh, p was a function of rho. Rho itself is rho 0 plus some epsilon correction.
Okay.
When we take a gradient of this p, we should differentiate it. This is dp over d 0. So p is some dp over d rho 0. dp of rho 0 over rho 0.
So is the first derivative between the point which is fixed, which is it's like the first order coefficient in a periodic function.
Yes,
Okay.
yes. So, and this derivative defines the speed of sound. Okay. So here we have dy squared minus dz squared delta rho, it equals to 0. Mm. Uh, uh, so if so if there is some time dependence, we can actually remove this term by changing coordinates, which corresponds to changing the frame. Like we can start moving with speed u0, and this turns into just a t derivative. But if we are solving different problem, if we if we ask for solutions where rho depends only on x, y, and z, so it's time independent, like like we are looking at stationary flow in some configuration. Uh, So in this case, this dt derivative, sorry, I actually forgot x derivative, dx squared minus dy squared minus dz squared. So if you consider stationary flow, then this t derivative disappears because delta rho is time independent. So it is delta rho of x, y, and z, not of t. Uh, then we get what? We get uh, 1 minus u0 over c squared times dx squared plus dy squared plus dz squared acting on delta rho equals to 0. And this is it. In principle, it looks like the usual Laplace equation, but the problem is that the type of equation changes when we change the speed of this flow. If u0, because it was dt minus this squared minus minus Laplacian. So it is precisely this one. So when u0 is less than c, it is a subsonic flow, and it is just a Laplace equation, or maybe Poisson equations, better to say. I forgot what is the precise name. And if u0 is greater than c, it is a supersonic flow. Uh, uh, And in this case, we have opposite derivative in front of the x squared. So it is a wave equation, but coordinates are not t and space coordinates, but one of these coordinates effectively plays a role of time. And physical intuition to this is the following, and that maybe I can draw it in this corner. So when e0 is less than speed of sound, we have some object which moves in the medium and creates some perturbations of this medium, and so they can go faster than the object itself. So these waves of uh, waves uh, of perturbations look like this. So it's, Uh, and it if you study more dispersion equations, you will see that it looks like equipotential lines of uh, mm, some field. But if u0 is greater than c, like this is the trajectory of motion of this object. Like it's a wave emitted in the previous moment of time. If it moves faster than the speed of sound, then the picture will look like this. So this this fluctuations emitted in the previous moments of time, and mm, this object is called Marcon. So mm, mm, and we will also see such a behavior from the study of the wave equation, which appears in this case. Like here we have non-zero fluctuations in the whole space, but here there is some domain, like everything except this corner, where these fluctuations are zero, because the waves has not have not reached that points yet. So for me, it looks actually quite surprising that planes can fly both at speeds less than the speed of sound and bigger than the speed of sound, because in the low situations, these two situations are quite different. Mm. Like we literally switch from Poisson equation to the wave equation. Mm. So maybe, uh, so are there any questions about this? Mm, check the camera. Yeah, yeah, and so far we have not seen any examples of diffusion or heat equation, or except this one. But let me now uh, show a few other examples which uh, give a continuous and discrete heat or diffusion equation. So let us consider the problem about random jumps. So suppose that we have some integer lattice, maybe on a torus, well, maybe on a circle. So suppose that we have some points, probably on 0 over the n, but it does not matter. So we can close this. Uh, And there is some probability to jump to the left, to the right, probability delta p to the left, the same probability. And the probability to stay in this point is 1 over minus 2 delta p. So let us compute, let us make the system also discrete in time. So so let us say that it is time t, and this is time t plus delta t. And so what is the probability to find a point at to find some particle at point um, x um, and point x at a time t plus delta t? It consists of three pieces. One possibility that we find a particle in this point is that it just stayed there. So it is 1 minus 2 delta um, delta p, p of tx. And other two possibilities are that this particle were in one of the neighboring points and it jumped to this one. So this equals to plus delta p times p of t x plus 1 plus p of t x minus 1. So and now it's kind of a heat equation or diffusion equation discrete in both variables in t and x, but we can still use Fourier transform to solve this. But because all of them are shift operators. But if you want this semi-discrete equation, we can say that delta p and delta t go to 0. But delta p over delta t equals to gamma, some jump rate or probability to jump in very small time delta t is gamma times delta t. And in this case, what we get? We get that dt of p of tx equals to to gamma p of t x plus 1 plus p of t x minus 1 minus 2 p of tx. So, and we get precisely this latest discretization of the second derivative. But and if we allow jumps, if we consider multidimensional lattice and we allow jumps in different directions, we will get multi-dimensional Laplacian. So, and we can also consider continuous limit of the system. And so And of course, since it describes this random jumps, it is similar to diffusion and also to heat, which has the same nature. So it's not surprising that that continuous equation also describes that situations. But if you want to derive the heat equation, uh, we should say that uh, uh, heat flow is proportional to the gradient of T, plus minus cap gradient of the temperature. And we should also write a continuity equation like dt of temperature plus divergence of J equals to 0. And it will give us maybe actually heat capacity times temperature. So if we do this, we get precisely dT temperature equals to kappa over C Laplacian of temperature. Actually, I forgot to tell this at the moment when we studied heat equation with wrong sign here, that there is of course a very important example of such equation, which is a Schrödinger equation. Equation of the free particle. And it looks like I h bar d psi over dt equals to minus h squared over 2m Laplacian of psi. And as you might remember, if this coefficient is purely imaginary, it does not lead to divergent Fourier transform, and we can find a green function of the Schrödinger equation precisely in the same way as for the heat equation. So this Fourier transform can be computed. So are there any questions about what I told already? So there is, of course, another example of the wave equation. It's equation for the waves in strings, in a string. So namely, let us say that there is some string which ha which has a tension T, and it has some linear density lambda. And now let us look at some element of the string which is of size delta L. We can consider a small uh, uh, a small deviation from the straight string. So uh, so we want to write a second second Newton's law for this element of a string, and it will look like so. So we have some z coordinate and x coordinate. So this Newton's equation will look like a d of lambda delta L times z, or maybe better to write it like lambda delta L dz squared over dt squared, which is the acceleration of this element, and it should equal to to a sum of the projections of the forces F1 and F2, which act in the opposite directions. So it will be F1 z minus F2 z plus F2 z. But now, what are these projections? F1 z is equal to t times z over dx, and computed at the point let us say that this is a point x0, and these are points x0 plus delta L over 2, and that one will be minus delta L over 2, and F2 z will equal to t dz over dx x0 minus delta L over 2. with a minus sign because it acts in the opposite direction. So if we combine this together, then then we get what? Using the Fourier series, we will get that lambda delta L d2z over d squared equals to t delta L d2z over dx squared. So, in other words, lambda over t d2z over dt squared equals to d2z over dx squared. So we obtain the wave equation for the string. So are there any questions about this? So, and if you want to add, if you want to make this equation a Klein-Gordon equation, like to add some term which will be proportional to z, we should imagine that this string actually lies in such parabolic potential. So we have not only this force which is proportional to the second derivative of z, but we can also organize a force which will be proportional just to z. So we can imagine a picture like this. So we have this uh, this kind of volley, and we put a string inside of it, so that um, the force which acts on the element of string is proportional to this plus also something or minus something times z. It's kind of harmonic oscillator plus x derivative term. Maybe that's all. Actually, I wanted to tell that you may remember that we studied also a discrete Laplace equation. So in situation where this equation appears is when we try to consider some lattice made from conductors and study electric current in this lattice. So if you combine Ohm's law and Kirchhoff laws, then equation for potential in the nodes of this lattice will be precisely discrete Laplace equation. And the right hand side of this equation will be the current flowing to each of these points. So, but you don't have time to derive this, and probably you can try to do this at home. Maybe I can do this as an exercise. So are there any questions about this? So, but I think it's the only lecture about physics. So all other lectures will be about PDEs themselves. So next time I'm going to tell how to find green functions for other equations. And also, probably you know that. Okay, thank you. Probably you know that 2nd of November. I don't remember is it working day or not, but system will be closed. So it's maybe next Thursday, right? Hmm. Okay. So thanks for the attention.